Imagine an electron in an atom. Classically, they're thought of as moons orbiting around the nucleus, but this meant that the electron lose energy through emitting photons and spiral into the nucleus. In proving this model, scientists represented atoms through probability clouds, meaning an electron's existence is smeared in reality. This is quantum mechanics. Quantum mechanics solved many issues with classical mechanics, but it also introduced randomness and made particle motion jumpy and discontinuous, which clashed with Einstein's theory of relativity. This was a problem because these particles move at nearly the speed of light, so to describe them, special relativity must apply. To unify quantum mechanics and special relativity, we need to reimagine the quantum world through quantum electrodynamics, or QED, which magically resolves these conflicts with elegant math. We consider a universe like a sort of room, space-time, which contains fields, the electron field and the electromagnetic field. Photons are disturbances within the EM field, and electrons aren't like marbles, but rather disturbances within the electron field. These fields can interact with one another, transferring energy and momentum, explaining the interactions between photons and electrons. QED describes the interactions between electrons not like tiny magnets that magically repel one another, but rather with the exchange of virtual photons. Imagine electrons like battleships, shooting one another, pushing themselves and the ships they hit backwards. The cannonballs are like the photons, giving us the interactions between electrons, transferring momentum between ships. It is important to note that these photons are called virtual because they're not actually there, instead placeholders for mathematical equations. It is useful to describe these complex virtual interactions in Feynman diagrams. Consider a graph of distance versus time. Each junction is an interaction between the particles in the EM and electron fields, such as an electron and a positron annihilating into a photon and vice versa, or an electron or positron absorbing or emitting a photon. Let's examine a simple diagram. We see two electrons traveling forward in time. One emits a photon, and the other absorbs this photon, causing them both to deflect. However, these diagrams are not descriptions of reality. We can only observe the particles entering and exiting, and everything in between is kind of a mystery. Since we cannot observe these interactions, it's kind of doing everything at once, a superposition of all possible diagrams. Since there are an infinite number of diagrams, we must use perturbation theory to figure out what will happen. Because each junction decreases the diagram's probability by a factor of 100, at a certain point, their contributions to an interaction becomes inconsequential. To solve this otherwise impossible problem, we'll then consider the most probable cases, allowing us to get a really good approximation of what will happen. QED's accuracy helps us predict the behavior of exotic particles, such as predicting positron motion in PET scans to find cancer. The success of QED motivated quantum field theory, which uses similar virtual particle exchanges to explain weak and strong force. Quantum field theory, along with relativity, have served as a basis for all of modern physics, and has given us the most precise understanding of the universe that we have.